Good afternoon, ladies and gentlemen. My name is Yu Wang. I'm a doctoral student from Institute of Mechanics in Chinese Academy of Science. It's my great pleasure to share my latest research in progress with all of you here in Peking University. And my topic today is the IDDES simulation of the combustion hysteresis effect in a dual-mode scramjet. And my report mainly contains this 5-part. And let's begin with the background. Throughout the history of aircraft development, from subsonic to hypersonic, it seems that the eternal pursuit of human being is for an aircraft which operates faster and higher. To achieve this, we need more advanced propulsion systems. The conflicting requirements between the high cycle thermal efficiency and the low energy losses dictate that certain engine has its own operation range. For example, in this for example, in this graph, the ramjet must operate in Mach 3 to 5, while the scramjet operates when Mach exceeds 6. The dual-mode scramjet consolidates the advantages of these two engines. It can achieve high specific impulse in wide range of flight Mach numbers through combustion mode transition. This dual-mode concept has been fulfilled in the last century. However, recently, in the most famous X-51 and the CIA and NASA scramjet, both suffered from severe inlet onslaught in their real flight test. Thus, the most important problems in the DMSJ is to guarantee a stable and controllable mode transition. However, in recent years, combustion hysteresis effect is observed during the combustion mode transition. Hysteresis is an inherent property of a nonlinear beastable system. For example, the combustion system in a DMSJ. It is defined as that the same flow parameters under different historical paths can produce multiple combustion solutions. It is certain that this hysteresis will cause difficulty to the active control of the DMSJ. However, currently, the mechanism of the combustion hysteresis is unknown, and its effect on the DMSJ performance is also unclear. Additionally, the massive computational cost for hysteresis raise higher requirements for the application of physical models. As for the turbulence model, the IDDES strategy with a two-equation K omega SST model is applied. In a boundary inner layer, a range type equation is adopted, then it switches to LES in massive separation by means of the IDDES length scale. In previous studies, U-range strategy is mainly applied to save the nearly unacceptable computational cost for hysteresis. But whether this method is suitable for flows with massive separation is debatable. Thus, in this study, we applied the high-resolution IDDES strategy for the first time in the literature. As for the calculation of supersonic reactive flow, the first problem is that the spatial-temporal scale of turbulence and chemical reaction is comparable. Thus, the high-efficiency traditional turbulent flamelet model is no longer suitable in this case. The second problem is that the scalar fluctuation, as circled boxed here, is high enough to be comparable to unity. Thus, the high-order pulsation terms cannot be ignored, and these terms are also quite hard to be modeled. Thus, the basic foundation of dynamic zone flamelet model is to decouple the turbulence chemistry interaction zone by zone. Mathematically, by using a conditional decomposition, the fluctuations in a divided zone is greatly reduced, as shown in this graph. Thus, the source terms can be strictly closed by ignoring the high-order pulsation terms. The whole computation is carried out on an OpenFOAM-based solver, which is mainly coded by my mentor, Professor Wei Yao. It is a compressible reacting flow solver based on the second-order hybrid KMP central scheme. This highly integrated solver can simulate the CFD problems associated with turbulence and combustion, multi-phase flow, and thermal non-equilibrium effect, etc. Okay, then the third part, case setup. The DMSJ in the University of Virginia is chosen here. The geometry is simple and classic. It includes an isolator, a combustor constant area duct, followed by a divergent duct. An unswept ramp is chosen as the flame holder, and the fuel is injected on the ramp base. In this study, we set 6 fuel conditions corresponding to the 6 ER values in this graph from 0.06 to 0.17, and the ER increasing and decreasing path is based on these 6 values. According to the grid independence verification, we adopted the 51 million cells in the following studies. Additionally, we adopted a detailed 13 species, 33 reactions, hydrogen chemical mechanism to better capture the dynamic behavior of the flame. Then the code validation. From the injection wall pressure profile, the numerical results matched well with the experimental data in all the 4 cases, and we successfully captured the 2-peak trend of the pressure profile. Then the fourth part, result and discussion. Here we make an animation of the temperature and the pressure contour in scramjet and ramjet mode. You can have an intuitive comparison of the combustion field in these 2 modes. From the above streamwise Mach number profile, you can also clearly classify the 2 combustion modes. If the flow is everywhere supersonic, the DMSJ operates in scramjet mode as ER equals to 0.06 to 0.14. Otherwise, the DMSJ operates in ramjet mode as ER equals to 0.17. This slide shows the temperature distribution. We can see that the flame is mainly stabilized in the shear layer following the ramp trailing edge. It is also noteworthy that the flow uniformity is worse in the ramjet mode because of the upstream pseudoshock structure. Basic understandings of the combustion mode transition can be obtained from the one-dimensional control volume analysis. Let us focus on the first equation. The static pressure on the left hand is mainly associated with the area relief rate and the heat interaction rate on the right hand. And the positive or negative of the right hand is determined by the unity minus the square of the Mach number on the denominator. Once the area relief cannot contain the thermal occlusion because of the heat addition to the supersonic core flow, an adverse pressure gradient arises and the pseudoshock initiates in the divergent duct as depicted in the figure B. As the heat release increases, this shock will propagate upstream and the combustion mode eventually transform into ramjet mode as this shock located in the isolator. With this understanding, we can move on to the combustion hysteresis phenomena. Numerical results observe an obvious hysteresis loop. From the instantaneous pressure contour, we can discover the large discrepancies in the pressure distribution for the same ER on the different passes. We then analyze the mixing and combustion efficiencies under hysteresis. The solid line here is the increasing path, and the dashed line is the decreasing path. We first look at the increasing path, the solid line. We can discover that the efficiencies keeps decreasing in scramjet mode as ER equals to 0.06 to 0.14. However, the efficiencies increases greatly as the combustion mode transforms into the ramjet mode as ER equals to 0.17. As for the decreasing path, the efficiencies increases monotonically. So when comparing the solid line with the dashed line, we can figure out that the efficiencies on the decreasing path is higher than that on the increasing path. So we can make a conclusion here. The hysteresis is mainly caused by the high efficiencies for the same ER on the decreasing path. Furthermore, to obtain more insight into the mechanism of the hysteresis, these two important problems has to be discussed. Firstly, why the efficiencies for the same ER is higher on the decreasing path. Two main factors may account for this. From this graph, it can be figured out that the mixing time scale on the decreasing path is evidently shorter than the solid line on the increasing path. Similarly, the compressibility level in the shear layer on the decreasing path is smaller than that on the increasing path. Thus, these two quantitative index explains the mixing enhancement due to the pre-combustion pseudo-shock structure in the ramjet mode. Secondly, the shorter ignition delay time and a well-initiated chemical reaction explains the more favorable initial combustion conditions provided by the former combustion state. Okay, the second problem, the maintenance of the pseudo-shock in the isolator when decreasing ER from 0.17 to 0.08 in ramjet mode. Let's go back to this slide. It is clear that under the decreasing path, the pressure in the combustor is much higher than the increasing path in the middle for ER values. However, when we focus on the decreasing path, the pressure in the combustor keeps decreasing and the pseudo-shock keeps moving downstream when we decrease the ER value. So, why this shock can locate in the isolator and it will not go back to the same as the increasing path on the left. And numerical results observed a regulation mechanism between the upstream shock structure and the downstream combustion zone through the middle subsonic region. The combustion field in a ramjet mode is simplified in this figure. Oscillations can be propagated upstream and downstream in the form of acoustic wave, and the response timescale of the upstream going acoustic waves is estimated here as the 0.89 flow flush through time. As we mentioned above, the back pressure in the combustor will first decrease as the ER decreases. Then the shock structure moves downstream to match the back pressure. Meanwhile, the fuel penetration depth increases, and then the mixing and combustion efficiencies increases, resulting the increase of heat addition. And this heat addition will in return raise the back pressure and then follow the variation. So the blue arrow and the red arrow here means the two competing physical process that helps the pseudo-shock maintain in the isolator under decreasing path. So when you see this graph, the black solid line is the pseudo-shock location profile, and the red line is the penetration depth profile. When we modicate the black line to according to the response timescale to the blue line, you can see a simultaneous variation trend of the blue line and the red line. The last part, we analyze the effect of combustion hysteresis on DMSJ performance. The total pressure loss is larger under ER decreasing path, in that the Rayleigh loss is bigger due to more heat addition. This discrepancy becomes smaller as ER decreases. As for the thrust of the engine, numerical results observe the thrust catastrophe under the ER increasing path, while no large scale of variation is witnessed on the decreasing path. So we can make the conclusions. In this study, we accurately predict the combustion field in a DMSJ and observe the combustion hysteresis effect as well as in the experiment. Secondly, we carefully discuss the reasons accounted for the formulation of combustion hysteresis and its underlying mechanism. Last but not least, we analyzed the performance of DMSJ under combustion hysteresis effect. And that's all for my report. Thank you.